Yes, before we start to fill this matrix K, we need to compute the area because we have the integrants in the matrix already, which are the product of the gradients. But we need the area of each mesh to perform the integral. So A is equal to, this case is going to be a zeros, the number of elements. So that's for K equal to 1 to 38. So what is the area? Is the cross product of these two vectors, right, of P1 minus P3 and P1 minus P2. So let's copy what we had. What? I thought, okay, I'll paste this here because we want the these, and we basically need the AK. I want to say it is equal to the absolute value of the determinant of the matrix we had here. Is that right? Huh? Oh yes, I want to take half of that value divided by 2. So yes, I'm taking the determinant here because that is the that's the cross product between the two vectors P1 minus P2 and P1 minus P3. That is going to give us the area. Okay, so we have a matrix A. Let's inspect it to make sure it looks roughly correct. 0.25. This is positive. I think it should be on the right magnitude. We'll see. Okay. So we have the area now, and I think we are ready to fill the stiffness matrix K. Okay. So let's do our assignment. Yes. Yeah, but in this case, I do want to loop over the elements because what I did is programmingly is more convenient to loop over the elements because I can split this matrix into contributions from all different elements. So for each element, I'm going to evaluate what the nodes are correspondingly and add the contribution. For example, the contribution to the I1 entry of the matrix is going to be K I1 is equal to K I1 plus. I'm doing plus here because when doing the loop, previously I may have already added value into that entry. Now it is an increment. And the increment is AK, right, is the area times the inner product of the gradients of itself. So it is the dot product of gradient of K1 column, G of K1 column. Right, is the gradient. Okay, so fine. And K of I1, I2 is equal to K of I1, I2 plus AK times dot product of GK2 column, GK2 column. Okay, and if we change this to 3, I made a mistake here. It should be I2, A2. Okay, and okay, let me reinitialize K and for this loop. Actually, you know what? Let me make a file so that it's easier to make K 2D. It's easier to make changes if we mess it up. So K is equal to this. That's initialization. Okay, and for K equal to 1 to the size the size of K1. I want to say I1, okay. I want to loop over elements, yes, thank you. So it's the size of points, right? And it's the second dimension. I want to say I1, I2, I3 equal to that one. Size of P, yes, thank you. Yes. Okay. You guys really helped me a lot. So I want to say the contribution to I1, the contribution to I2 is equal to this. You know what? Actually, I can do a mini loop over here. I can do actually for I goes from 1 to 3, right? I can actually do this is going to be my I1 to 3. Okay, I can do a mini loop here. I can do j equal to 1 to 3. I can do k of I1 to 3i and k and I1 to 3j is equal to the same thing plus dot dot dot. I want to go to the next line, ak times the dot of these two gradients, k and I and column, k and j and column. Is that right? Can I do that? I think I'm fine, so that I don't have to write all these 6 entries of the matrix. That is like the contribution of one to another. Right, 1, 2, 3, 9. 9, yes, and 3 of them are duplicate, right? So it's because of the symmetry. Okay, so I think I'm fine now. Let's run this, make K 2D. Now I have a stiffness matrix K. Let me file it. Close. Okay, so that's what my matrix looks like. Because it's an unstructured mesh, like it's not tridiagonal, it's not pentadiagonal, it's just sprinkled around. But we still have a diagonal entry, and we should get the same thing as in 1D, which means the diagonal entries should be positive, and the off-diagonal entries, they should like, well, I can't say anything about the off-diagonal entries, but most of them are negative, right? I can't guarantee them as being negative, like in the 1D case. In the 1D case, it's the product between two gradients of different signs, but in this case, I can't really guarantee them to be negative. But like it's good sign, a lot of them are negative. All right, so I get the matrix K now. What else do I need is the B, right? The matrix B, in this case, would be the integration of f, which again we assume to be 1 times the phi, which is a linear function within that interval. So instead of the area of a triangle, it is going to be the volume of a tetrahedral. Okay, which I think the formula is a third times the area, right? Third times the area. So okay, so basically we'll be accumulating like the third of the area for the B's. So let's do a, I don't think we need a function for that. So let's say we have a B that is zeros. How many points do we have? 130. Why do I 136? Okay. Okay.
working. I go from this to this, copy, paste.